All right, so this week we are doing the 5 slides, sort of kind of annual program, where what we do is we have 5 intrepid physics faculty prepare slides for a real presentation that they could kind of actually do, at least are supposed to be able to. And then those slides are given to someone else who is been suddenly told, oh, you are presenting these slides because this person couldn't make it and you're the pinch hitter. And so here's their slides with 0 seconds of warning. Go for it. And so that's the way 5 slides works. In fact, it has kind of evolved a little bit to where the slide creators have gone out of their way to make the slides a little bit more challenging than you might normally expect in a seminar. And that's all part of the fun. So what we're going to do is we're going to have 2 competitions going today. Competition number 1 is going to be who did the best job presenting somebody else's slides. Competition number 2 is going to be who made the best slides for the 5 slides competition. I will be putting up an anonymous poll for the for our 5 slides contestants, and those contestants are in alphabetical order: Dr. John Armstrong, Dr. Brad Carroll, Dr. Colin Inglefield, Dr. Adam Johnston, and Dr. Stacy Palin. And so they're going to be our 5 intrepid contestants. The question now is who presents whose slide? All right, so to do that, I'm going to change this over to a screen share, and we have the Wheel of Fortune. And so here is the 5-slide Wheel of Fortune. They will each have about 8 minutes to present their slides. And so let's go ahead and spin the Wheel of Fortune and see who comes up first. Dr. Armstrong comes up first. Okay, so I will put him in at the bottom here. So Dr. Armstrong will be presenting Dr. Palin's slides, and we'll find out in a little while if they're still married. All right, so let's remove him from that, and let's spin it again. And it's Dr. Inglefield is going to be presenting Dr. Johnston's slide. And we're going to take and do that again. And so spinning a number of time here. And Dr. Carroll will be presenting Dr. Inglefield's slides.
Oh no.
Yay!
And here we go. Dr. Palin will be presenting Dr. Carroll's slides. I'm so sorry.
Oh, I'm so pleased. I'm so pleased.
And that leaves Dr. Johnston as our first presenter for the slides created by Dr. Armstrong.
Oh,
wait, so I go last?
You go last. So the order of
Okay.
the presenters, the order of the slides will be Armstrong, Carroll, Inglefield, Johnston, Palin in alphabetical order. The order of the presenters will be Johnston, Palin, Carroll, Inglefield, Armstrong. All right, so that's what we're going to do. So we're going to go ahead and get started with that. I need to fire up Dr. Armstrong's slides. We're going to transfer and I have not looked at any of these slides. So if they don't run, don't blame me. But
That's part of the fun.
That's serious self-control, man.
it really was. All righty, so let's.
Also, if the slides don't work, it's the creator's fault.
Yep.
But it's the presenter's problem.
yes.
I'm going to hand control to our first presenter, Dr. Johnston.
Oh no, 5 slides. Here we go.
Let's see if I can find him in here. There he is. So, Dr. Johnston, it is all yours.
All right. I suppose I should have something to present too.
See, it's not showing up. Oh, yeah, you know what? It probably isn't. Hang on just a moment. I'm working on all the details here.
So by the way, John is the first 5 slides presenter. This was all a joke. And John's presenting 5 slides right now.
All
Great.
5.
There we go. Now,
Ah,
Oh my
now,
gosh.
Adam, you should be able to control it.
now I see. I have full control. I'm positive.
This is
Thank you.
I'm
Thank
gonna-
you so much for this opportunity to present my, this is, I should admit, this is a new line of research for me. I'm just beginning to really fully understand it myself. And so I'm welcoming you into this, my own kind of trajectory into XR integration in high flex multi-format physics, quasi-physics environments. Which is you've not heard of this because I created it myself. And this is, of course, some ongoing research. It's longitudinal and case study in extended augmented virtual reality core educational delivery modalities and higher learning flexi virtual settings and the relationship to the physics curriculum at Weber State and beyond. So it's got some limited application. But we'll see if it's something that we can actually see, maybe some other additional application to places outside of the XR and maybe to the YR or even other kinds of institutions like Utah State or who knows where. So let me get started and welcome you into this this research. Let's see. If I push a button. So you may be asking, what is XR? In fact, I've asked this myself multiple times and recently especially. XR is extended reality. It is augmented reality. It is virtual reality. None of this makes any kind of sense until you really start to grasp the X in XR. X marks so many spots. X is really about extension and extra and most of all, extraordinary. And that's really what I wanted to create here, is something that was really extraordinary so that we could provide our students, provide our learners, provide our faculty with something that was not just ordinary, but something that went far beyond, because that is, after all, what you deserve in these extraordinary times. You need extraordinary solutions and not just regular reality, but beyond the extra reality. So let's start with that basic, very clear definition that I've provided for you and see what else XR can do for you, as I'm sure this next slide is going to show us. I tap the buttons. Oh, there, it worked. So here's how it worked in our study. Deploying the co-learning organized virtual integration database, over 600 million college students from 192 countries enlisted, and I put enlisted in quotation marks because enlisted suggests perhaps voluntary. This was not a voluntary study. Most of the time we get IRB, human subjects approval for these kinds of things. This extraordinary, extra kind of situation didn't require that, and it didn't require it because we didn't ask for it, nor did we actually care that we were doing anything ethical, because really in these days, this day and age, what is ethics, really? So we went ahead and inserted with our regular sample of folks here, we inserted, these are all the controls, and here's the experimental condition right here. We wanted to see what would happen to a student who wasn't maybe as well prepared as most, a student who perhaps isn't as qualified for the position he might be in right now, or a student who just needs that little bit of extra encouragement. And perhaps this extraordinary reality is going to be just the thing for this particular individual. We'll see. This is experimental, so we're not really hopeful that we can do anything for this individual, but you never know. Let's see how it all went. So the results are, and as you can see over here, this is our experimental condition. After the propanol started to wear off, he's still a little bit groggy. And he couldn't really see where he was going. We had to, over here, these are radiation barrels. We had to redirect him to other places, but we gave him these protective placebo bracelets. The placebo bracelets would protect him from alpha, beta, and gamma emissions from these radiation barrels over here. You can see when we put him in this particular condition after everything wore off and we tested him versus the controls, that he did absolutely terribly. There were not just error bars, but just errors all over the place. You can see that's what error bars are. It's just how many mistakes you made. And there's just all kinds of this experimental, extraordinary subject was just rife with human error. It's just an error of human. It was a disaster, and we should have had IRB approval for this, but let it be known that from now on, we'll seek out human subjects approval. For all, I should say, if you find this individual, you can pick him out because he's the one with the long cable trailing behind him. And he's just wandering around the parking lot with these blinders on. Help him out. Take this thing off and show him to his car after he kind of orients himself again. So anyway, I want to conclude by saying this is not the end of the work that we're doing. There's still plenty more damage. I mean, plenty more experimenting we could do. And we could start, not just putting goggles over people's eyes to help them learn physics, but we could actually, strap them down, for example, put them in a learning environment that we can actually control. And potentially, we keep doing these stupid simulations of launching people in space, but we have a good sense that we could actually launch someone into space. So it's not just virtual reality, it's reality with a double X on the extraordinary. And then these individuals could go into orbit, and they could finally actually test out the idea that they could experience a sense of weightlessness even in a gravitational field as they orbit around the Earth. And that's where I think learning really is going to reach some kind of apex until they come crashing back down to Earth. We forgot to do the human subjects approval, and the engineering wasn't quite right. But that's what science is all about. So thank you for attending the seminar.
All right, so that was Dr. Johnston. Let's all give him a round of applause. Woo! We're going to hold questions off till the end. And so our next presenter is going to be Dr. Palin, presenting Dr. Carroll's slides. It's going to take me a moment to get my mouse back here. I got to abort control from one person and get to another. So give me a moment to bring up the next set here. And stop that share. All righty, so coming on to our next presenter. So Palin presenting Carroll's slides. So those were Armstrong slides. These will be Dr. Carroll's slides. And let's see, oops, nope, wrong button. All right, now let me change the share. This is all taking way longer than one would like. All right.
This is the best part, John. You're totally making this part up. This is hysterical. This is awesome.
All righty. And all right. Dr. Palin has control. And so it's 5 slides again. Go for it.
Right on. Well, thank you so much for inviting me here today to your virtual seminar. I'm so delighted to be here. And today I'm going to talk to you about logarithmic aging and general relativity. And my plan during this seminar is to give you the real experience of how time dilates as you have new and different experiences that are maybe less interesting than others. So that's my whole point today, is to really give you a kind of interactive experience here in the virtual Zoom reality that we now all live in. So you may have noticed, not all of you, probably the undergraduates have not yet noticed this, but certainly the faculty have noticed, is that time passes more quickly as you age. And it's very important to ask the question, is this a perception or is this actually what's happening? Are older people actually aging faster than younger people as they get older? This is an important question. And so when you're young, an event occupies a larger fraction of your life, so it can seem to take longer. And so, you got to ask the question, is this perception or is it reality? So we'll go to the next slide where we actually begin our study. And we tried this out ahead of time, but it seems that I cannot get to the next slide. So while John is working on that, okay, great, super. Thank you, John. Here we go. So first of all, let T naught be the objective time. And that's the time measured by some objective observer like your child or God or your dog. TP is your perceived subjective time. That's what you perceive as the rate at which time passes. And you know from being in physics class that sometimes time passes very, very slowly. And other times time passes very, very quickly. So that's your perceived subjective time. So the logarithm of the rate at which perceived time passes is proportional to your age at that point in objective time. And I'm sorry, there's an error in these slides. This shows the natural log, and it should really be log base 10, because I'm an astronomer and I do everything in log base 10. So there should be a log base 10 here and then a conversion factor inside to convert the logs. But we'll just go on. We'll just pretend that it's actually natural log, even though it isn't. So here we have the natural log is proportional to the time T naught or T0, the objective time. And then you can go ahead and you can express that otherwise by taking the exponential of both sides and turning it into a differential. The minus sign on the right is there because perceived time passes more slowly, so the derivative has to be negative. If you integrate this from T equals 0, what time is that? Right? Okay, everybody wake up. Follow along. T equals 0. So this is birth time to some final time, T, which would be?
Later.
No, we're not going to go there. Okay, to get your total perceived age at the objective age, T0. So TP is equal to L. This is a constant, a calibration time that sits out front, times 1 minus e to the negative T naught over L. And this equation should look familiar to you from all of your studies of population dynamics, for example. L equals 215 years to match a 20% slowdown at age 100. So one thing that we have done is we've gone and asked Brad Carroll, who has ages ranging widely, much, much longer than anyone else in the physics department, to give us his perception of what 215 years was like, and relate that to his current age of, well, an order of magnitude more than that. So, and so we've added that into the equation, and sometimes we put it in with the L. Okay, next slide, please. Okay. Does this make sense altogether? Of course it does. And you know that it has to make sense because not only do we have a graph with a shaded area, but we also have a graph with data with error bars that do not line up on the line. And usually that's when we know things make the most sense. So our error bars in this graph, where we have the bottom graph with subjective age on the vertical axis and age of the respondent on the horizontal axis. Now, this is a longitudinal study of one person formerly in the department. And then in order to do this for Brad Carroll, we had to actually multiply all these numbers by 10, but then we just took that 10 off because it was cleaner on the graph and the horizontal axis got crunchy. So, but we got a very similar result for his much more advanced age. So when t0 equals 0, your perceived age is the same, because you were just born, so no elapsed time has happened. So those two things match up at that time. But then your perceived age begins to be noticeably less than your objective age, around 40. Can I have a show of hands, please, of everyone who has noticed this effect? Okay, all thinking, right? Some people have noticed it more than others. Go ahead, by moving your hand closer to the camera, show me how strongly you feel that effect. Very good, super. Yes, so that matches up exactly with the graph. I love it, perfect. When t0 equals 50 years, your perceived age is 5 years less. But then as you get older to t equals 100, your perceived age is only 80, which is baby compared to 100. Next slide, please. So it's important to notice that acting your perceived age can be dangerous, because if you go around acting like you're younger than you really are, you can get into all kinds of trouble. And in particular, you can get into all kinds of trouble with other children who are able to do things that really you can't do any longer.
Uh-oh.
So
33.
if we could bring your perceived age in line with your objective age, that would be great. So we'll go to the next slide and see how to do that. Whoops.
Oh.
So what just happened there is that the slides disappeared into a black hole, and that was an example of exactly how I was going to finish the talk. So in gravitational time dilation, you have the opposite effect, where the time actually seems longer. And so that can be used to cancel out the effect. And in summary, what science says that we should do in order to counteract this effect is we should basically take all the baby boomers and stuff them in a giant rocket and shoot them into a black hole to bring their perceived age more into alignment with their actual age. We're now seeking funding for that, and we hope to get that going pretty soon. Thank you very much. Are there any questions?
Nope, you get to do your questions at the end.
Oh, right,
So,
questions at the end.
Don't know what happened there. So
Thank you for
kind
your
of showing
attention.
slide. All right. That was weird. So I think what happened is you got screen control finally somehow, and we both clicked at the same time. And
Bye, Boomer.
All right, our next speaker is Dr. Carroll, who will be presenting Dr. Inglefield's slides. And so we'll get that going as well here in just a moment.
I will say that Colin did give me a preview, and I know this is something really near and dear to my heart. And
He gave you a
so
preview?
He did.
Oh,
He did. I know exactly what's coming.
that's cheating.
John, it's precognition.
No, okay. All right.
All right, I'm trying to find you in
Disqualification.
the long list here.
Disqualification.
Okay, so Brad, you should have control. So what is actually showing up on our screen?
Is what I'm seeing is the last slide of Stacy's talk,
Okay.
which is really exactly what she talked about anyway, which I find amazing.
All right, how's that?
Okay.
Pretty awesome.
Okay. This is indeed near and dear to my heart. Stacy pointed out that in my slides that I had erroneously used the natural logarithm instead of the base 10 logarithm. And she has unfortunately replaced a B with a Z, but they sound alike, but that's okay. So this should really be okay boomer, but it's not. So here we go. It's a transition to remote learning and the late mid-career physics professor, a technology enhanced multimedia case study. Okay, well, if this is technology enhanced, then I'm going to ask John to do all the controls for me because I don't know anything about technology. But let's go on anyway, and we'll see what happens. Oh, look at this. I love, for students out there, this is good technique for presenting a talk to always have an asterisk. See the asterisk down there? And I'm pointing to the asterisk. Pretend I'm pointing to the asterisk, although I'm pointing toward you. And look, down here down there is this incomprehensible little blue box. Backpack and top hat are trademarks of Coxwell Cogs and Spacely Sprockets. Great Jetsons reference. So go on, and down below here we see there are 4 more slides. This is the first slides. Okay. Introduction. So please watch this 90-second introductory video. Again, notice the multimedia aspect of this. So this is sort of a meta talk. I'm not going to be talking about the content of the talk. I'm going to be talking about the presentation of the content of the talk. So the contents of this, what it's on the screen, is really irrelevant. I'm going to be talking about its presentation. So look at how well this is presented. What we have here is a picture of, first of all, because this is just, up-to-date media, we have down in here what looks to be like a picture of a film camera. And I don't know quite what that is about. And so we're going to watch this introductory video, which I can't click upon, but I bet John Soul can. Okay, look how fast that's moving.
Kaltura is down.
Kaltura is down.
Clicking on it moves you forward.
Okay, so apparently Kaltura is down, and again, because this is a meta talk, not about the content of the talk, but about the presentation of the content of the talk, I just want to point out that this is something that often happens. And when that happens in a real class, you're going to have several minutes of lag time. And so you just have to back and fill. Basically, you just have to stall for time. And there are many techniques for stalling for time. One of them is to simply talk about stalling for time. And that tends to be a very effective technique for actually stalling for time. But let's move on to this. This is the 3rd slide. I've stalled now for enough time. Okay. Case study, part 1. Whoa, let's go back. Yes, thank you, John. Okay, this is the 3rd slide. It's always helpful in the lower left-hand corner to tell your audience where you are in your presentation to let them know how much longer they have to stay awake. Now, here we have on the left this late mid-career professor may be overwhelmed by technology. Okay, and there will be struggles in the first however long it takes. And the truth is, and you should expect this when giving a talk, is that there will be struggles no matter how long your career lasts. Nothing but struggles, because the rate at which new technology is invented is much faster than the rate at which you can master technology. And so you can never be up to date. This is fantastic, because it means you never have the illusion of competence. So let's just move on here. But you can see that here is this handsome layout. And here's another little, oh, look at that. On the right, there's a picture of our late mid-career professor with a little arrow on it. Wonder what happens if you click that. Go ahead, John. Oh, look, I have no idea what just happened, but apparently clicking these little little arrows does nothing but advance to the next slide. And that's what's called a trap. You see, if you put traps on your slides, you can get people to click it and then go to the next slide when they're not expecting to. So this is fantastic. So let's just sit back and look at this screen and just look at how good it is. First of all, you have to go to great expense to do this. You just can't do this on the cheap. And our mid-career professor here has hired a hand model to give him a perspective here, and he's demonstrating parallax. Now, if this person who has the thumb, if you hold your thumb out and you look with one eye, you'll see column on the left side of your thumb. And if you look with your right eye, you'll see your thumb covering up column. And you'll have to decide which of those is most beneficial. Also, there's another pseudo video here, trap, of Colin standing on a chair looking down at a pillow, wondering, how can I get down to that pillow? He's lost his instructions on how to get down. This happens with late mid-career people. And fortunately, he's going to measure how far it is down to the ground so he can calculate how fast he'll be falling when he hits the ground to know if anything bad will happen to his ankles. Always very important. So this is the fourth slide. I don't know how much time I have left because I haven't invented, it's hard to tell. Is that time left?
1 minute.
1 minute?
It says one minute on the timer. It's 2:04, Brad.
I'm not sure that's helpful. But let's go on to the last slide because I think this all needs some summing up, this meta talk on not the content of the slides, but on the presentation of the slides. So here's case study part 3. This is the all-important feedback. Now, for those of you who may never have given feedback on a presentation, let me tell you how feedback works for the case of, say, an online course. What happens is that you ask your students to give feedback, and maybe out of 100, 10 do, 5 because they like the course, and 5 because, yeah, they have a grudge. So that immediately ends you up with an average of 3. But it really doesn't matter what the numbers are because those numbers go into a computer report somewhere. And that computer report is never seen by anybody. So please don't worry about this. Now, I would encourage you all for your actual online physics courses, say for anybody, especially if that person doesn't have tenure yet, to just rate them 5. And if the scale goes up to 7, rate them 7. Because why not? I mean, you're not going to change anything they do anyway. So, give them a break. Now, so what you should do is rate this presentation using either Top Hat or Backpat app. Now, if you don't know what Top Hat is, I can call them with your phone number. And then you will be bothered by calls and messages from Top Hat from here on to eternity. But that's okay. But make sure and do this. Remember to, if you're going to shop at Lowe's, because more people at Lowe's wears masks than at Home Depot. And here's a picture down at the bottom of some guy for some reason. And we must say that this is the last slide. Thank you. I've enjoyed talking to you about not the content of the talk, reminder, but of the presentation of the content of the talk, which does not include my presentation of the content of the talk. Thank you very much.
All righty. So that finishes our set of slides that were created by Dr. Inglefield and presented by Dr. Carroll. Okay, so let me, for some reason, I lost my controls on that one. We'll see what happens with the next one. So these slides are created by Dr. Johnston and will be presented by Dr. Inglefield once I get the system up and running, hopefully without it losing track of things. So give me one moment here. And every time I change Zoom a little bit, it rearranges all my windows. So let's see.
You've got this nailed, John. This is so funny.
Where are we at here? That's this one.
This virtual slides.
All right. Okay, click to start. Do I have control now?
You have control, and that's your first slide.
All right, excellent. Okay, I'm having a little trouble reading that, so I'm just going to adjust my chair a little bit. Perfect. Okay, so I'm going to be talking about how to teach physics, and it's really all about offering students what I would call a unique perspective. So there's a traditional way to teach physics where we sort of have all the letters right side up, but we can offer students a different perspective if we just flip that. And the flipped classroom is really, it's the newest thing. I really recommend all the instructors out there try it if, you know, if you're confident enough. So, all right. Can I? Oh, wait a minute. I'm trying to go back. All right, I was looking for slide number 2 here. Whoa. In the flipped classroom, you occasionally take breaks from content altogether. Just freewheel. So
The screen share is down.
screen share is down. Okay. Well, any chance that I could get that back?
Adam, can you just hold up handwritten notes?
Oh, here we go. Here we go.
Oh, there we go.
All right. So like I said, in the flipped classroom, you'd like to present physics contents in multiple different ways. So a lot of sort of what we might call old school, say early late career physics instructors write Newton's law as F net equals ma. In the flipped classroom, we flip the m and write A equals F net over m. And it really provides a whole new perspective. I remember, you know, just you have this epiphany where you say students, they're like, hey, Dr. Inglefield, I'm really confused by this F net equals ma. And I say, well, what if I flip it? What if I say A equals F net over m, and then that's it? Got it, right? I see Laura had it. That was the moment when she decided that she was going to pursue her degree here at Weber State University. All right, next slide, please. In the flipped classroom, you have to allow students opportunities to explore physics in their own environment. So here we've suggested that students either get a cat, or we have loaner cats in the department that they can pull up to a little drive-through in the loading dock, roll down their window, we toss the cat in their car, they can take the cat home and perform various experiments on it in the comfort of their own home. So, next slide, please. it's really important in the flipped classroom. And here you see a really nice example of the flipped classroom where we've written words facing both directions on either side of the model here. So it's really important in the flipped classroom that we give students a taste, an appetizer, if you will, of the real world applications of physics. In this case, the real world application is, suppose you are concerned about your reading glasses in an electrical storm. I'm in an electrical storm, Dr. Inglefield. Do I have to remove my reading glasses? What if I also want to read? No problem. You put on one of these Faraday cages, which is really a protective cover for your reading glasses. Then you can safely read and be out in an electrical storm at the same time. No problem whatsoever. Real world application all goes back to A equals F over M. Next slide, please. In the flipped classroom it's really important to use good visual aids. And if you know, as I look at this particular graphic here, what it really illustrates about physics is the interconnectedness of everything. See, there's all these lines going all over the place. It's not just F equals MA, it's A equals F over M. It's not just V equals IR, it's I equals V over R. It's all connected, people, all connected. That's what all these lines are really telling you. It doesn't even matter the sort of what all these individual symbols mean. That's not the point. The point is the complexity and connectedness of science. That's what we're trying to do. That's what we're trying to get across in the flipped, modern, evidence-based, superior learning environment that is the Weber State University Physics Department. I think I'll end there.
All righty, so that's, I think I discovered what the problem is with our slide program here. As soon as I give control, since I've got 3 monitors and a lot of real estate going here, as soon as somebody moves their mouse just a little bit, they start flicking other things. And that's been causing some sort of mayhem.
So are you going to control and I'll just tell you?
Sure.
Okay.
I think that's the most successful way. So we're professionals here. Don't try this.
Are we?
All righty. So our next, that was, first of all, that was Dr. Johnston's slides presented by Dr. Inglefield. And our last
2 different people.
Behind door number 5 is Dr. Armstrong getting ready to present Dr. Palin's slides. So let me bring up Dr. Palin's slides here and we'll get that presentation going. Maybe. And so we've got that. And check this. And there we go. You should have it. You are ready.
Okay. Let me just take a moment. So I haven't left my house in 235 days. So I'm really happy to be here right now. And since I haven't gotten a chance to talk to you all for quite some time, I just wanted to take a minute to say something that I've really been heartfelt meaning to say for a long time to all of my colleagues. And it's important, and it's just your grandmother from there. Thank thank you. That's all I'm trying to say. So I'm tearing up a little bit after that, but I appreciate your time. So today I wanted to talk to you about one of the most amazing places I've ever had a chance to visit, and that's Action Park. And in particular, there's a place in Action Park called oh, this is fine. It's all good. Action Park Physics really is the most dangerous amusement park in history. It's in a place called New Jersey, which if you've never been to New Jersey, it's the spot that's right between New York and Colorado. That's New Jersey. Pretty much stretches from the Mississippi River all the way to the Gulf of Mexico and into northern Saskatchewan. So that is New Jersey. By a show of hands, how many people have, sorry, I gotta take this off. It's getting a little warm in here. Okay, that's all right. How many people have been to Action Park? Show of hands. Okay, all right. Next slide, please. Okay, so my favorite ride at Action Park is what's called the Loop-de. It's not called the Loop-de-Loop because there's only the one loop. And if you look at how this works, if you slide down from the top, the sound you make as you go down is "Oodah," and then out again. So it's the Loop-de as you fall out. But if you look at this is a classic conservation of energy problem, right? I mean, you start at high potential energy, you then fall to lower potential energy. That energy has to go someplace, right? And you figure, how high is that roughly? Somebody give me a roughly, what do you think that's 14 meters roughly? Okay, so 14 meters. How fast do you need to be going to get out, right? But then, of course, the problem is friction. Now, if you, in particular, a special type of friction called butt friction, and it's called butt friction because if not for gravity, you'd fall, but friction keeps you from falling, right? So that's why we call it butt friction. All right, next slide, please. So let's see what happens when this goes out of here. Gosh, it's really getting warm in here. I said next slide, please. I said can I have the next slide, please? Oh, it is the next slide. Sorry. Okay. So analyzing friction. So if we think about how friction works, butt friction is just a coefficient of friction, just like anything else. So we take the amount of work that you're going to do, which is how much force you need to drive you a certain distance, and from that you can figure out relate the force to the energy, and then if you know what the energy is, you can relate that to the friction. Of course, we don't like to think too hard about that. In particular, people like me who do a lot of computational stuff, this involves some calculus and it's not interesting at all. So what we're going to do instead is just go down the ride. So we got a whole big team of people together to go down this ride, and they're still there. You can see the part where they all get stuck. And you could have seen this coming, Action Park, because they flow water down this to keep you falling, but for friction, right? They keep the water going down, but the water isn't going fast enough to spin all the way around. So there's a little dry spot at that top part, and that dry spot is where everybody's still stuck. So moving on to the next slide, please. Now, this is the most exciting thing that I've had a chance to talk to you about in a long time. They've done a new and improved Loop-de, and it's a 30 femtoton loop. You might wonder what that means. What it means is that you don't need very much water to lubricate the entire loop, okay? Because you only need a femtoton of water to go all the way around, and so you don't have to rise it that high. The other thing is they've replaced the hill with a vacuum injection tube on the bottom side. Okay, so the vacuum injection tube, what they do is they put you in there and they cap it, and then they evacuate the tube, and then they pressurize you through. So you're sure to make it through, regardless of how challenging your fall would be, but friction. going around there. So the question that I have for you is, what's the cutout for? Okay, there are no answers.
The vacuum.
That's fine. Thank you. You have to put the vacuum on, but as we all know, vacuums pull. So how do you keep the person from coming out when you're trying to evacuate the tube? This is one of the bigger problems, okay? So no one's actually ever ridden this thing, but it looks really cool for the advertisement flyers, and you can get people to come out by just putting this on the loop. So next slide, please. Now, I have some personal experience with this. Thermodynamics is one of my favorite topics. It's been a favorite topic of mine. And one thing, if everybody knows, just looking at the word, thermo means, hello, is anybody there? Is this muted again? Sorry, this is muted again.
Heat.
Oh, it was muted before. Okay, I get it. All right, so thermal means heat. I heard heat. Thank you very much. And dynamics means
More
Not
heat.
stop.
so it's thermal magnetism is the whole thing that we're talking about here. And what we have here is an electrified chute, and somebody comes down it very, very quickly. And they used to, if you look at the bottom, when these things were first built, they used to use little sleds. Now they don't even bother. I mean, you can see up at the top, because it's magnetic levitation, you don't need little sleds. But you can figure out how fast you need to be going in order to deliver heat if you happen to be touching it, but you're not, because you're being magnetically levitated by the dynamo. So you're dealing with the thermodynamics. All right, so I think I'm just going to stop there. I mean, I'm leaving you with an extra credit question. It has to do with how much alcohol spray you're going to need to alleviate the burn before they invented the magnetic levitation action park thermodynamo slide. So I'll go ahead and stop there. I think I've gone over time anyway. But thank you for your time. Thank you for your attention, and please visit Action Park in the great state of New Jersey. Was that
All right,
muted
let's
the
give
whole
them a
time?
round of applause. So we have our 5 contestants. We started out with Dr. Johnston presenting Dr. Armstrong slides, then Dr. Palin presenting Dr. Carroll's, then Dr. Carroll presenting Dr. Inglefield, Dr. Inglefield presenting Dr. Johnston, and then finally Dr. Armstrong presenting Dr. Palin's slides. And so the big time is here, and that is to see if the poll will work. So let's launch the poll. So the first question is, who was the best presenter? So now is your chance. You should be seeing that. We'll give it about 30 seconds here. We've got 36 of 46 votes in. We still have a few more people that need to vote.
Nickelback. Nice.
All righty, and let's see, almost everybody's voted. We got 89% of the votes. Let's see if we get 90%. Come on,
I had to
someone
vote
else has gotta
twice.
vote.
You're voting for me.
All
Wait,
right.
you can see the results?
I can see that.
I
All right.
can't see the results.
Oh,
No, you can't see the results. Okay, so are we ready for this? Here is
Yes.
the results of the 5 slides presenter. So you should be, I don't see anything. Are
What?
you seeing results? All right.
That's impossible. Colin Inglefield wins it. I've never seen anybody give such an expressive talk with just his hair.
I used to try and give
I'm
talks with
honored.
my hair, but then I ran out.
Congratulations, Dr.
Thank
All
you.
right,
Thank
so
you.
Dr. Armstrong wins that one. So let's go ahead and stop that one, and let's go to our next poll. So let's see here if I can get that one to now go away. Now let's go to our next one. Uh-oh, how do I get to the next poll here? Here we go. Here, right. So now, which was the best slide deck?
It might be good to have a quick rundown of which one was which by title.
Okay. Let's see. I'm not sure I can do that quickly. The last slide deck was by Dr. Palin. The first, let's see, actually, those of you who, Dr. Armstrong, which was your slide deck by title?
XR reality, XR study.
Okay. All right. Dr. Carroll, what was yours?
Logarithmic aging and general relativity.
Dr. Inglefield
Was okay Zoomer.
and Dr. Johnston,
Was how to teach physics.
upside down, and Dr. Palin, our New
Action Park.
Jersey professor.
Action Park.
All right, so there we go. There's your reminder of whose slides were which. I don't think I'm allowed to vote. I got you.
It doesn't let the host vote.
No, dang.
You can be a tiebreaker, John.
I can see the votes though. There's not going to be a tie, I don't think. All right, we've got 91% of
And
the votes.
that's
are in.
why you don't get to vote.
Okay, so it is with 93% of the votes in, then we'll say that 93% of the precincts are reporting. We'll end that and share the
Let's
results.
call it.
And Dr. Johnston is our winner.
Yay! Woo. Action Park
Alrighty.
number 2.
So there we have it. So thank you everybody for joining us for our mostly annual 5 slides. It was a great way for you to lose forever an hour of your life.
Never coming back.
All righty, everybody. Have a great day.